Hello everyone. So we will continue our discussion about distance vector routing protocols. And remember, in the distance vector routing protocol, each node tells its neighbors essentially what information is there in its routing table. So the routing table has destination, next hop and cost. And what the distance vector protocol does is it shares these two columns with its immediate neighbors. Okay, so everybody knows the distance from its neighbor to any particular destination, and using that information it finds out which of its neighbors is closer to the destination, and it updates its own routing table based on it. Okay, so that's what we covered in the last class. But we said that no particular node has the full topology of the graph of the network, because this information doesn't tell you exactly how each node is connected to its neighbors and so on throughout the network. You just have some vague idea of the distance of any particular neighbor to its destination, okay, to any particular destination. So there are problems that come up because of this, and the main problem is the count to infinity problem, because of which we have routing loops. So let's take a straightforward example. So suppose we have node X connected to A, which is connected to B, and let's say that the distance, let's say the cost of these particular links is 1. So what do they have in their tables? Let's just write that down. So there's a destination, the next hop, and cost. So X knows that the distance to A is 1, and the distance to B is 2. So let's say everything worked out correctly. And what does A know? So A knows its distance to X and B, they are directly connected to it, and B has this information. So A and X, the distance is going to be 2 and 1. Okay. So this is all fine. It's a very simple network and with just 2 links, and these are their tables. Now suppose this particular link from X to A fails. So X to A fails. Okay. So what is going to happen? So A should send a message. A needs to inform B, and it says that my distance to X is infinity. Okay. And suppose that I say that this is message 1, and B is sending its routing updates. What it normally sends, let's say that B is sending this information in its table, the destination and the cause. So it sends, I beg your pardon, it sends this information x2, and of course it sends the other information here to a1, but we'll ignore that for the time. We'll focus on the information about x. Okay. So suppose these two messages are sent out sort of almost at the same time. Okay, so before B learned about this failure, which it would get to know from this message 1, it has sent out the second message. Okay. So what happens now? Okay. So in this particular case, okay, so B tells A A1 and X2, and A tells B X infinity B1. Okay, and they do that almost simultaneously. So let's see what happens now. So A's table has become, this has been removed, and this has been replaced by X infinity. Okay. But now A gets this information. So what does it do? It doesn't know the full topology of the network, so it thinks that B can somehow reach X, and the distance is 2. This is what A thinks. It doesn't realize that B is going to X through A. Okay. So what it's going to do is, again, it's going to remove this and it's going to replace it by XB, and so my distance to X, A's distance to X is going to become 3. Okay, so this is what happens. Okay, and meanwhile, let's say that B has got this information. So what is it going to do? It's going to see that A is not able to reach B. So A is not able to reach X because of this. So it's going to get rid of this, and it's going to say that I cannot reach X, right? So let's say that that's what happened. And of course the situation might be a little bit different depending on what message reaches when, right? But let's, for the timing, just let's say that this first set of messages went this way, and then the second set of messages came here almost at the same time. Okay. So this is their routing table now. And now what is going to happen? Okay, so let's say that okay, so let's say that A tells B okay, there's another routing update. So A tells B that my distance to X is 3, and of course right, my distance to B is 1. Okay, and B is going to let's say B receives this message and it updates, So what happens? So this is going to go away and it's going to say that I can reach x through A and my distance is going to be 4, right? And let's say after that B tells A that I can reach x with distance 4, and of course I can reach A. Okay, so what's going to happen now? So x sees that I have to reach x, A says that I have to reach x through B with distance 3, and now the distance of B to A has gone up to 4. So this has to be updated and this becomes 5. Okay, because B says I can reach x with distance 4 and my distance to B is 1, so my total distance to x is going to be 5. Okay, and so A tells B x5 B1, and similarly this changes. Because of that this is going to become 6. Okay, and so B tells A x6 and so on. Okay, and this keeps going on, and what happens is that this goes to 7 to 9 and so on, right? And this goes to 8 and 10. So this is called count to infinity. And what have we ended up with? So essentially A thinks that B is the next hop to X and B thinks that A is the next hop to X. So if at all there is a packet destined for X which A has, A would send that to B because it's the next hop, and B would again send it to A which it thinks is the next hop, and you have a routing loop. Okay, so this is a most trivial routing loop just between two nodes. They keep sending the packet to each other. And effectively this goes up to infinity, okay, which is why it's called the count to infinity problem. So because in distance vector protocols no particular node knows the entire topology, it's possible to have these sorts of routing loops. Okay, and it depends on exactly what happens at what time. Okay, but here in this particular example that I took, we saw how you might actually end up with a routing loop. So this is a serious problem, and one solution is that in any particular routing protocol, infinity is you choose this number to go to a maximum value which you consider to be infinity. You don't let it arbitrarily increase. So the routing information protocol, RIP, allows a maximum distance of 16. So the maximum cost can be 16, and if it reaches 16, then you stop. That is essentially considered to be infinity, that you cannot reach the destination. Implies you cannot reach the destination. Okay, so what would happen is that these routing table, these entries would both reach 16 over here, because of which if A or B has any packet for X, it will just drop that packet. We solved this count to infinity problem. So some solutions have been proposed in the past, and One of those solutions is called split horizon. So if we look at the previous example, we can understand what split horizon does. So basically B has a path to X through A. So what split horizon is saying, B should not tell A about his distance to X. He should just say that, either keep quiet about it or say that it is infinity. Okay, so that's the idea of the split horizon. And so let me precisely say what split horizon is. So the split horizon is in its most basic form says that do not advertise information about a destination to a destination information about a destination to a neighbor if that neighbor is the next hop to the destination. Okay, so the problem that is arising over here is that A thinks that there is a path from B to X because B is advertising to A, it's saying that X2, there's my path to X is of distance 2. And that caused the problem of a loop over here. Okay, that even when this link broke, A was sending it to B thinking B had this magical path to X. And B of course thought that the path was through A, and so we ended up with a loop. So what split horizon is saying is that B should not give this information X2 to A because A is the next hop. And let's see how that solves the problem in this particular example. So we have X A B. Let's say we are putting weights on the links as 1. Okay, the costs are 1. Okay, and now what happens? So now under split horizon, B does not tell A anything about X. Okay, so A has destination, next hop, and the cost. And let's say X becomes infinity, okay, and B has this information. And distance is 2. So since A is the next hop, B does not tell A this information. So under the split horizon, if we have split horizon activated, so what will happen when this particular link fails? This particular link fails. So the routing table of A gets updated because this link has suddenly failed. And A is going to tell B, it's going to say X infinity. And B does not tell anything to A about its distance to X. Okay. Okay. So X is not going to get confused that B has some path all the way to X. Okay, and B gets this information that A cannot reach X, that the distance has become infinity. So it updates this to infinity. Okay, and we don't have a routing. Okay, so this is a straightforward solution. And there's another version of this split horizon, and it's called split horizon with Poisson reverse. Which is very similar. So here in this particular case, B would actually tell A that its distance to X is infinity. Okay, so normally in the usual routing updates, it doesn't send that information. Okay, so it's not just when this particular situation occurs. So in all situations, you do not advertise information about a destination to that neighbor which is the next hop of the destination. Okay, so B in the normal split horizon, B doesn't tell A about anything about the distance to X, but in Poisson reverse he will say that my distance is infinity. Split horizon with Poisson reverse is doing something very similar to what we had earlier. So a node tells its next hop to a destination that its distance to that destination is infinity. So essentially over here, since B is going to X through A is the next hop to X, B will explicitly advertise to A that its distance to X is infinity. Okay. So B sends advertisements. Okay, so the term used is a routing advertisement when you tell your neighbors information about distances to various destinations. So B sends advertisements of the form X infinity to A. Okay, even when there is no routing failure or anything like that, it says that my distance to X is infinity. And in a more complicated network where there are many nodes, this will be done. So every node will tell the next hop in its table to any particular destination. Okay, so here A is the next hop to X, so it will actually say that my distance is infinity. Okay. So you can work it out, but this too will prevent routing loop occurring in the example that we just studied. Okay, so because A is not going to make a mistake of thinking that B has a path to X. Okay. So these actually solve the problem of routing loops in these very trivial sort of cases, not in general cases. So when you have a routing loop consisting of just two nodes, it's definitely going to prevent a routing loop like this forming. But when you have a larger network, this may not work. So let's look at a particular example. So let's say we have three nodes connected this way in a triangular fashion, and there is a fourth node X over here. And let's say that the costs are 1 everywhere. So what are they going to have in their tables? Destination, next hop, and the cost. So this is at A. It's going to have BCX. So in this case the next hops are BCX and the cost is 1. What about at B? We have distance, next hop, and the cost. So we have ACX and the next hop is AC, and here A is going to be the next hop. And what does C have? Well, it has destination, next hop, and cost. So it's connected to AB directly, and the cost is 1, and the distance to X is 2 via A. Okay. So now let's suppose that this particular link actually fails. And so let's say, so what's going to happen? So A is going to send a triggered update. It's like an emergency update. So it says that my distance to E is to X is infinity. And it sends it to B and to C. Okay, but let's suppose that this message gets lost, the one which was sent to C. Okay, so this might happen. Okay, and there may be other scenarios even when the message is not lost, where we may end up with a routing. But let's just say that this message is lost. Okay. So B learns that I cannot reach X now through A because this has become infinity. Okay. So what's going to, let's see what B is going to do. So given this information, he is going to update his routing table to this, and he is going to send out this information to C. Okay. And okay, so let's just write that down. B sends X infinity to C. Okay. And so suppose we are using split horizon, so that means C is not sending information, let's say to, or we could do it either with split horizon or split horizon with Poisson reverse. But let's say that we are using split horizon, so C doesn't tell A about anything about its distance to X. Okay, so C is silent about X to A, and B is also silent to X about X, is the distance to X, when it sends information to A. Okay. But however, C tells B about its distance to X, because B is not the next hop to X, right? A is the next hop. Okay, so C tells B, it says that my distance to X is 2. Okay, and C uses split horizon. So it does not give distance to A. Distance about X to A. Okay. So C is silent, it doesn't tell X, so we were trying to avoid the routing loop which took place in the first example. But C gives this information to B. So B thinks that there is some path from C to X which is of distance 2, which is actually not true over here. So what's going to happen over here? So this is going to get changed, and so C puts this information in its table, or B puts this in its table. Okay, so this is in B's table. And now what is going to happen? So I beg your pardon, so this is C over here. Okay, so this is the current status. Okay, and this has also been removed. We have X infinity here. Now what's going to happen? So we are using split horizon, so B is not going to tell C this information because C is the next hop. Okay, so what is going to happen? So if B thinks that C is the next hop, C thinks that A is the next hop, and of course A currently doesn't have any information. Okay, but B is allowed to tell this information to A because A is the next, not the next hop to X anymore. So B tells A, it says that my distance to X is 3. Okay, and so after that this is going to get removed, and A is going to have X, B, 4 as the distance. Okay, and now A cannot tell B this information because it is using split horizon. Okay, but A is going to tell C it says that my distance to X is 4 now. So now we see that we are we've created a loop, and there's also count to infinity problem over here. So C realizes that this is no longer valid. So A is still the next hop. It's not hearing about X from B because split horizon is being used. So it sees that A is my next hop, but the distance has gone up to 4. So this has to be changed to 5. Okay, because it imagines that there is a path all the way from A to X of distance 5. Okay, and it's going to update that information to B. So this is also going to change. So B thinks that C has a path of distance 5 to X, so it makes this 6, and this is going to go to 7 and so on, right? And we have a count to infinity. Okay, so A thinks that B is the next hop, B thinks that C is the next hop, and C thinks that A is the next hop. So we have a routing loop of this kind. Okay, and if at all a packet meant for X was sent by A, it would go in this route. Okay, it would keep going around in this route. But of course, if we use something like RIP, these distances will quickly reach 16, and they will realize that they don't have actually a path to the destination, because 16 is considered to be infinity. Okay, so distance vector has these problems, and the split horizon and Poisson reverse ideas only solve the problem to some extent, but not completely. So like I mentioned earlier, there is a routing protocol called RIP, Routing Information Protocol, which uses distance vector. And in this particular protocol, the cost of every link is assumed to be 1. And 16 is considered to be infinity. So it's sort of like we are saying that 16 is equal to infinity in our routing table. So if at all we have a count to infinity problem, we'll reach 16. And so the particular host will know that it doesn't have a path to any particular destination where the total cost is 16. Okay, so this sort of reduces the problem of routing loops, because after some time we realize that there is a loop. I mean, the count to infinity problem has gone all the way to 16. I mean, it doesn't go all the way beyond 16. Okay. But the shortcoming is that you cannot have very long paths and very large networks if we have something like 16 here. Okay. So what if you want to have a network which has more than 16 hops? Then this is not going to work. Okay, so RIP can be used in smaller networks, and distance vector protocols have some advantages in that they are very simple. I mean, the way you update the distance to any particular destination is quite straightforward. You just look at the distances from your neighbors to those destinations, and you just add your own distance to the particular neighbor, right? And there's nothing very complicated to do over there, right? So I would say the advantages of distance vector they are simple and easy to implement. Okay, there is no complicated graph sort of an algorithm, no depth search or DFS or BFS or anything like that. Okay, so it's very simple and efficient. Okay, but there are disadvantages. So count to infinity, problems, and accompanying routing loop issues. Okay. And also the convergence of the routing tables can take some time. So what I mean here is that I'm not talking about any link failures or anything like that. So let's say that there is a large network, let's say hundreds of nodes, let's say, and lots of links between various nodes. And let's say that we switch on all the nodes in this network at the same time. Initially, each node only knows about its neighbors. It doesn't even have a routing table containing all possible destinations. And slowly it learns about nodes which are further away. But it takes some time for the routing table to become fixed, for it to get converged to something or the other, right? Even when there are no link failures. Just because it takes some time to hear from your neighbor about their neighbors, and then to hear from about the neighbors' and so on, right? To nodes which are quite far away. So, though it's very simple, there are these few issues because of which sometimes people go for another type of routing protocol which is based on link state routing. So here let's take an example. Let's say we have A, B, C, D, E, and let's say we have this, and suppose these are the costs on the various links. Okay, so normally what information would be shared? So suppose normally, let's think what would D send. So D would send information about its distance to all nodes in the network, but to its immediate neighbors. D would only talk to its immediate neighbors over here, and that's in distance vector. But it would send lot of information, essentially its cost to all the other nodes in the network, but to its immediate neighbors. Here we do something different. So here D would just send information about its neighbors. It would send the local topology information, but it would broadcast it to everybody in the network. Okay, so each node sends to all others. So this is a broadcast. Information about cost to immediate neighbors. Okay. So what, as an example, D sends this information that I am connected to C and to G. It sends this information to everyone. Okay, so it's not just to its neighbors, it broadcasts it to everybody else. Okay. Okay, so it's sort of like a flipped version of distance vector. So distance vector, you told your neighbors, only your neighbors, but you told them information, a lot of information about your distance to everybody in the network. Here you're telling everybody a little bit of information about whom you're connected to and what are your distances to them. Okay, so this local information is sent to everybody else. So that's actually very good because A is going to hear this information from D, so it can reconstruct this part of the network. B is going to tell A about all these 3 links that it has, so it can reconstruct this part and so on. So effectively, A is going to have information about the full topology in the network. and that is going to help A essentially find the shortest path using any standard technique that we have. So link state routing uses the Dijkstra algorithm. So this is something you would have studied already in your algorithms course. Okay, so you're given a full graph, and each node is going to find its shortest distance. Essentially, it's going to find a tree in this network, which is going to connect it to every other node in the network. Okay, and the paths in that tree correspond to the shortest paths to any particular node. Okay, so we'll just write that down. So each node finds the shortest path tree to all other nodes in the network. Okay, so you're familiar with how this is done. So we'll just take one example and close with that, right? So let's say that A has this full topology and it wants to find the shortest path to everybody else. So what is it going to do? So it's going to look at its let's draw it this way. So A has this information. It initially starts with its immediate neighbors. Okay, so let's say that T is our tree. T is, let's say first we start off with A. Okay. And what are we going to do? We're going to choose whichever neighbor is the closest, which in this case is F. Okay. So what we end up with is this. That's one link, and we just increase this set to AF. Okay, and now we add all F's neighbors too. So for every node there in the set T, we add the links to its neighbors. Now we have to add G also, and now we do the same thing. We find what is the shortest path within from A to all other nodes over here in this subgraph. And of course here, let's say that we choose this one, so the distance is 3. Okay, so T is going to become AFG. Okay, so we have added this link also. Okay, so we've grown our tree. These two links belong to the tree. Okay. And now what do? We repeat the procedure. So now we have to add the neighbors of G also. Okay, everything that is there in T, we have to add. Okay. And now we want to find the closest node to A within this, among all that are there in this subgraph, which are not there in T. Okay, so the distance to D what are we going to have here? It's going to be 2, 3, 4, 5. Okay, and distance here is also 5. So okay, I beg your pardon. Okay, and but we haven't yet chosen this, so we have to choose that. We have to choose E next. Okay, so the distance is 3. Okay, and we proceed in this fashion. So now, since we've added C to the tree, we've added this should have been C. We have to add okay, so this is going to continue, and so we end up adding D. Okay, that has distance. This is going to be the shortest distance, so this is going to be shorter than this one. Okay, so this is going to be a distance 4, and then what are we going to do? We've added nodes up to distance 4, and then we add this one. Okay, this distance is 5. And what about to B? B is the only one remaining, so this distance is going to be shorter. Okay, so our tree is going to look something like this. So we're going to have A, C, E, B, D, F, G. Okay, this is going to be our shortest tree, and I'll just write the weights over here. Okay, so after C we add D, and then we add let's see, we could add E or we could add B, right? Okay, so finally we have this. Okay, so this is something you would have studied extensively in your algorithms class. Okay, so and this is going to guarantee that any path in this tree to any destination is the shortest path. We will not be able to find any other path in the graph from A to any other node which is shorter than the distance shown over here. There is no path from A to D, for example, which is of distance less than 4. Okay, so A is going to be able to run this particular algorithm because it has the full topology, the full graph of the network. So what does A create? So A is going to have a routing table. So it's going to have a destination and it's going to have a next hop, and it's going to have the total cost. So let's see, so we have B, C, D, E, F, G, and given this tree it just has to find what is the next hop. So for B the next hop is going to be C, the cost is 5. For C the next hop is going to be C. For D the next hop is C. For E it is E again, and for F it is going to be F, and G also it's going to be F. Okay, and this is the cost. Okay, so each node is going to get all the information, the full graph, and it's going to run the Dijkstra's algorithm, and it's going to create this table. Okay, so if A gets a particular packet which is meant for G, it just has to look up this table and see that F is the next hop and forward the packet to F. Right, and similarly if it gets a packet, let's say for D, it just has to forward it to C and forget about it. Right, and the protocol is going to work fine because C also knows that its shortest path to D is along the distance is 1. Okay, and it will go along this path to D. Okay, so everything is going to work fine, and we don't have to worry about routing loops over here. Okay, when a link fails, what do? So let's say that link from A to F fails. In this particular situation, A is going to send this information to everyone. So they broadcast to all that their link has failed. So of course this is absent from the particular graph. Okay, this particular link has failed, but I'm assuming both A and F are up. Right? For some reason, let's say the wire got cut. It's possible that F itself as a node fails, in which case both of these links would be effectively failed because A would not be able to communicate with F, G would not be able to communicate with F. Right? So they would broadcast this information. Let's say both A and F are alive. They would broadcast that there is some update to the graph that this link has failed. So what do they all have to do? For example, A has to rerun Dijkstra's algorithm. Okay. So all are going to. So each of them broadcast this. All are going to rerun Dijkstra's algorithm. Okay, and quickly, assuming that this Dijkstra's algorithm runs pretty fast, depending on how large the network is and so on. Okay. They are going to quickly find again a new shortest path tree. Okay, and everything would be consistent, and we wouldn't have routing loops. Okay, so Dijkstra's these particular link state protocols are a little bit more complex in that the algorithm is more complex, but the advantage is that you don't have routing loops over here. Okay, so no routing loops are count to infinity. Problems, okay, and convergence of routing tables is fast. But the disadvantage compared to distance vector is that the algorithm is more complex. Than distance vector. Okay, so typically if you have a very small network where you don't care too much about the count to infinity problems, where because the count to infinity will very quickly reach, let's say 16 in RIP. In that particular situation you could use something like RIP or a distance vector protocol. But if your network is larger, you might want to go for a link state protocol, because if you use distance vector, there may be routing loops which last for quite some time. Okay, and also the convergence time is longer. Okay, so if you have a very large network, you would expect once in a while one link to fail. If you have thousands and thousands of links, you should expect a link once in a while to go down. And with the distance vector protocol, it's going to take a lot of time for that information to sort of propagate throughout, and for the routing tables to converge. Whereas here, very quickly, information is broadcast and everybody reruns Dijkstra, and then there are no more any loops. Okay. So for larger networks for intra-domain routing, we would want to use link state routing. But if you have a small network, you might want to go for something like RIP, which is a distance vector based protocol. Okay, so that's a little bit of theory about intra-domain routing protocols. But the question that I want to address in the next lecture is what to use as the cost. So throughout here we have just treated it as almost an algorithms problem, and you have some costs, and you just use Bellman-Ford or you use Dijkstra's and you come up with the shortest path. But what should we use in practice in networks? Because if you think about it, maybe initially there are no packets going on any of these links, but after some time you have lots of packets, and let's say that this particular link is getting congested, there's a lot of traffic going in here. Then what should we have? I mean, should we have a weight of 1 here or not? Because there are too many packets going here, maybe we should discourage people from forwarding on this particular link. And if we want to do that, how would we do that? By changing the link weights. Okay, so if you have a high link weight like over here, it's very unlikely that this particular link would be part of some shortest path. Okay, like for example here, this particular link AB is not there in the shortest path tree of A, okay, which is rooted at A. Okay, so if you want to discourage people from using a link, you would want to increase its weight. Okay, and the situation might change, from time to time. There may be more data packets on a particular link at one time, but then there may be less packets on a particular link. So in practice, we may want to change these link weights over time. So we'll discuss that problem in the next class, about how in practice we may want to set the link weights.